As I announced last week, today I would like to cover review the torsion theory. I hope that what we have covered in beam theory is quite enough for you to prepare for all tests. In other words, in chapter 11 and chapter 10 and chapter 11 is basically beam theory. Now we will review the shaft and torsional theory, basically chapter 8. And chapter 9 is also torsion theory, but this is mainly for thin wall shaft, so which we're not going to cover in this semester. So that will be covered next semester. Okay, let me see. I will briefly go through torsional theory. In any structures, of course, including shaft, when we apply torsional load, to calculate deflections, in this case, rotational angle, the applied load will be the torsional load, and deformation will be a rotational angle. And material property in this case will be the shear stiffness. And torsion load is should also have to meet the equilibrium. And inside material there is a stress, and of course a strain. And stress and strain, there is a relation. In this case, it's mainly shear stress, so there will be a shear stiffness. And a very important point in torsional theory is that we start with deformations, as like in beam theory. In other words, we define what kinds of deformation we would have in torsion under torque. So first we start with U theta, theta directional displacement, and R directional and Z directional deformation are all zero. Only non-zero component is the theta directions, and that is proportional to R and Z. So this is the most important assumption and a starting point in developing torsional theory. And then the rest of the procedures, like define strain and stiffness and stress, and defining all the equilibrium, which, in other words, which is the torsion is defined as the shear stress and integration of the cross sections. Okay, so please keep in mind, and this whole procedure is pretty much the same as the beam and the bar and beam theory. So this is the comparison between torsion and bar. Bar, in this case, bar is subject to a tensional load P, and shaft is the subject to a torsional load T. And the P, by definition, is the integration of a sigma axial stresses, and torsion is defined as the shear stress times R and dA. That's a torsional. And this one, these two equations, it can be called equilibrium conditions. And as you can see here, tension is generating tensile stress. I mean, in this case, is a Z, is axial stress, so we call them sigma ZZ. And the shear stress is causing a shear stress tau. So a tau, and stiffness is in E and G, and strain is epsilon Z and gamma, and the deformation is the UZ and U theta. So is important and very useful to remember both deformation, strain, and whole procedures. And the result is that delta under tensional load, deflection will deformation delta under of this bar, length L and cross section A, stiffness E, is a delta is simply PL over EA. And for the shaft, the rotational angle phi is given as the torsional load T and L divided by G and IP. And stress is simply force divided by A, and shaft shear stress tau is torsional T times R over IP. So again, there is a very similar analogy between those two theories. Okay, so torsion theory, as I mentioned, the shaft under torsion, and there are many different please turn off all your mic. Please, I don't know who turned on the mic. Please turn off your mic. There are different types of a shaft. There are different types of shafts, as you can see here. One typical shaft is the one a solid circular shaft. So and another one is a hollow circular shaft. These two shafts is certainly has a circular cross sections, and our theory it mainly applied to these two types of shafts. And non-circular shafts such as the rectangular and thin wall closed section shaft and thin wall open section. Open means that there is a slot, so it does not. They are not connected all, and the shaft with this kind of open section has very weak resistance compared to other closed section. But anyhow, in our torsional theory, we mainly focus on solid, circular, or hollow, closed circular shafts. Okay, and as I mentioned, we always need to start with the deformations. And here, this is the deformation observations. And this is the before deformation, and we have the ABCD, arbitrarily the ABCD cross sections. And under torsions with respect to a BC plane. So this plane will be fixed, and this the upper plane, which has the AD, will rotate. And this A will move to A prime, and D will certainly center of the axis. So D will be there. So this is after deformation. 마이크 끄라 그러면 누가 들어와 있니? 그 학생 이름 좀 적어요. 자, 학생들 마이크 다 꺼주세요. 마이크 다 꺼요. 자, U displacement field가 이런 그림을 어떻게 우리가 수식으로 표현하느냐. The point is that how to express this kind of deformation using mathematical expression. That's the one of the point here.
여보세요? 네네.
누구야?
저 꺼져 있는 걸로 아는데.
So the bottom, let's say the bottom surface is fixed, and U theta is defined as U theta is simply proportional to R and phi is the C times Z. So this deformation, okay, this deformation is simply, we can say that U theta is only non-zero displacement, and which is the proportional to R and Z, right? R and Z. This is so important equations. And once we have this one, the rest of them is very much straightforward. We have a strain definition. So we have a CR, C proportional to R, and stress and definition of the torsion. So finally, we have relations like this one. But the most important, as I already mentioned many times, is the these definitions. Okay, this is the definitions, and when we have, so this is the stress definition defined from displacement. And we put it here. And when we integrate, we have these equations. Now, a very important point here in this derivation is that this G and R and dphi dz. So dphi dz is always a constant and can come out of integrations. So this is the out of integration, but please pay attention to G. G can be out of integration when this whole shaft is made of one material. But this one can have several different materials, say G1 and G2 and G3, something like that. Then we can have many different, we need to have a different integrations. In here, we have to have G1 R square dA plus dA1. dA1 is the A1 here, and G2 R square dA2, and plus, for example, let's say we have three materials, G3 R square and dA3, right? And then dphi dz. This is a torque T. So in this region, in each region, G1 now is a constant, can come out of integrations. And so this one will be G1, and rest of them is, again, we can define I1 and G2 and I2 and G3 and I3. Well, if we have a multiple material, we can sum as many as the number of materials. And then dphi dz equal T. Okay, so please pay very special attention to these derivations. Okay, so this is the one we have. So main point here is that we got this dphi dz. Okay, dphi dz, we have T over these terms. Now, once we have this term, we can always go back to tau, and we can put this term here. So each one will have a, for example, we can have different shear stress here, here, here. So depending on materials, see, depending on the G, sometimes we have a shear stress is like that. If this is a bigger G1, and sometimes a shear stress like that, and sometimes a shear stress like that. And so tau can be discontinuous depending on the material properties. But I will redraw here. This one is the gamma, okay? Gamma is always continuous. Gamma is always continuous, but again, as I mentioned, this tau can be like that, and can be like that, or can be like that, because you have to multiply tau equal G gamma, okay? G gamma, G can be different from material to materials. Okay, basically that's a very brief review of torsional theory. And again, there is the polar moment of inertia, I. This is the one, pi over 2 and R04. And if this is a hollow, you can simply subtract inner polar moment of inertia. Okay. And now this is a torsional theory, and in our lecture note website, I uploaded some sample exam, okay, sample exam, midterm and final for last years, actually starting from 2006, 2007, and 2009, and 10, and 11, and as many as I could find. So I uploaded and hope you can find them and you can study them. And I select some of them, some of the problem, torsional problem. Okay. Okay, so this is the some of the problem I took from this previous exam. Okay, so as I mentioned, I upload many, all my previous midterm and final exam. Well, some of them are in Korean, okay? For example, I took one from a long time ago, 2006 and 2007. There is the problem regarding torsion theory. Again, I will define this problem, and then we will discuss tomorrow in class. Okay. Here, this problem, torsion T. Okay, torsion T is applied to here. Actually, there are 3 shafts connected in series, and each one, the length is the L, or you can consider them different with a different lengths and different G1 I1, and this is a G2 I2, and G3. Actually, this. Okay, I'm gonna rephrase. Okay, this is the same shaft. This is the G1 I1. Okay, so this is L1. So they are same, but in middle one is a middle one as a different shaft length and torsional stiffness, G2 I2, and then here we apply the torque. And now, how much angle it rotates where we apply this torque? Okay, that's the problem. That's the questions. And please try to solve yourself and hope to discuss tomorrow. Another one, which is very important problem, and now this one we have a structures. I will call them structures. The reason is that this right angle structures is subject to a torsional load here. Okay, we call M0. This is the torsional load. We apply the torsion here, and then how much it rotates angle here, where we applied this torsion. But we can call them torsion with respect to these structures, but if we look at this structure, actually the load we apply is kind of a bending moment. So we cannot call it torsion or bending. We just apply the moment here. So again, the question is how much it rotates, how much it twists, where we apply the moment. Okay, how much the angle twist, rotational angle. That's the one we want to calculate. Okay, and the length is the L, and here, of course, EI or GJ, and this is the EI and GJ. Is the same bending or torsional stiffness. Okay, so this is the very important questions. Actually, let's try to find a few more torsional problem in previous case. The one we got was from 2007, a long time ago, but the problem wise is pretty much new style. Now, how about the bending? I mean, the 2007. Well, not much. Here, we don't have problem related to torsions, but some problem has some midterm and final. It has not only questions, but also have all the solution. So will be very useful for you to prepare or review all the theory we covered. So for example, 2007 and first, there is the always solutions. Okay, even for the how much the point we assign for each questions. Okay, there's a 2006 and 2007 and 2009. Well, in this one, we have a stepped shaft as shown below, and we apply certain load moments, and this one can be one we can discuss in the class. And again, please try to practice yourself and or try to solve yourself. Okay. Okay, there is a final exam 2010. This is a 2010, and well, here, I mean, all the final midterm exam, you have a very interesting beam problem as well. But since we already cover all the beam problems, I'm not gonna go through all the beams, but for your practice, there are very interesting, or very good beam problems for you to review. For example, this one. And now here is the very important questions. It is like that. And here, torque T is applied to a closely linked member as shown. So, and calculate angle of rotation. And each member has a circular solid cross-section with a radius R and shear modulus. Here, again, the cross-section is circular, and this is also circular. And we have to say shear modulus G and tensile modulus E. Similar to a previous case, well, this part is work as the torsions or shafts, but this one will also this will work as a beam, bending beam. So the this one, if we look at it this way, say this one is the X and Y, and if we look at and the Z-axis, the Z-axis of vertical directions, Z and Y, then this one will, what will happen? This one will bend like that. Originally the straight, right? But this one will bend, and then this one will goes like that. So I will call A, B, and C and D. And so this is a C and D point, and this is the view in this direction. Pay attention to a coordinate system. Okay, and of course the shaft connecting AB is a twist. So this will twist, and this one. Oops, I'm sorry. I have to put like that. So like that. Okay, so this is the deformations shape, and the point here is to calculate how much the angle rotate where we apply torque T. Okay. Okay, let's do go through another one. There's a 2010. This is the, oops. No, not this one. And 2011, well, there is a just a solutions, and midterm, this is a block, and more circles, and this is the a tension, but we have multiple structures connected together, and there's a load. So this is a procedures. Now we have a question of the problem on the torsional theory, but again, this one is very similar to what we already studied. And okay, this is a very very good good case for you to review and then study. Okay, we with all the procedures. Okay, I'm not gonna cover the solutions, but you can refer to solutions. Okay, again, there are two shafts, and first shaft has the cross section and of the material A, and second shaft you have consists of two materials, and inside there is a material A, and outside is a material B. That is the second shaft. And shear modulus of A is the material A, okay, and material B is the this one. So shear modulus for each A and B is G and 2 times of G respectively, and the shear strength is a tau Y, and tau Y is the same. So it is important to know how much torque you can apply before yielding. Okay, so in this one, you have to calculate not only deformation but also stress to calculate to see whether they are yield or not. Okay, so very important questions. Okay. And 2012 final exam and beam theory, and oh, this is the one we already covered in class, right? And yeah, this unfortunately we don't have a torsion problem, but we have a very good bending problems. Okay, please review them. In 2012, there is a midterm, so there's a more circle and stress strain and failure and so on. So this is the solution sheet for that one. In our final exam, basically, main point will be on beam theory and torsion theory and failure. Okay, but when you solve them, you always need to understand the basic theory, of course. So you need to know the all equilibrium and stress and strain and Mohr circle. Okay, so I cannot say you all the problems for each chapters. Again, mainly beam and torsion and failure. Okay, so mainly in terms of chapters, the chapter 11. Chapter 11 and chapter 10 and chapter 8 and chapter 7. Okay, that is the main issue for final exam. But again, you of course have to know chapter 6 for the material properties relating stress, strain, and temperatures, and another chapters like chapter 5, stress strain transformation using the Mohr circle to, as you know, to find out whether material fail or not, we have to know the stress strain transformations. So none of the chapters can be skipped. But I can say that the final exam will be mainly on beam and shaft and failure. So I will write down here. I can say final exam in 2007, first semester. The exam will be on June 21, right? And at 7 p.m. on June 21, okay? And the chapters will be mainly 8. I mean, I don't want to say chapters, but mainly torsions and bending and failure, okay? But again, you need to review all the chapters, especially stress strain transformation, to understand the failure criteria. Right? So the test will be a closed book, okay, and no calculators is needed. There will be a 5 to 6 problems. And duration will be 7 to 70 minutes. Okay, this is the announcement for final exam this semester, and please review all the torsion theory we list here, and then to discuss tomorrow. Okay, any questions? Okay, so this will complete today's class, and see you tomorrow.